Copper is known to have antimicrobial properties. That should be known. If you come across this question in the homework, go ahead and click that link. It is very interesting to learn about copper's antimicrobial properties. You want to test the claim that the average lifespan of a COVID-19 sample on copper surfaces is at most 266 minutes. You carefully place samples of COVID-19 on 6 copper surfaces, find the average lifespan, and calculate the test statistic t equals 3.614. We want to find the p-value of the test statistic. So, first of all, let's find out what kind of test this is. Left, right, or two-tail. And there is a hint in the test statistic that I'll talk about in a moment. So to do that, we're going to find, first of all, the claim in symbols at most. At most means it can't be more than 266, but it could be less than or it could be equal to. So mean is less than or equal to 266. The opposite is the mean is greater than 266. Now the claim in this case gives us our H0 because it has the equal. So we say mu equals 266, and the opposite in this case then gives us the alternative hypothesis. That would be mu is greater than 266. The greater than in the alternative hypothesis tells us this is a right tail test. So right tail test means I'm going to want the area to the right of my test statistic into the tail. Now, if it's a right tail test, you should always have a positive test statistic. If it's a left tail test, you should always have a negative test statistic. And if it's a two tail test, well, then you don't have that hint. Could be either positive or negative. If it's a two tail test and you have a positive test statistic, you find the area to the right. If it's a two-tail test and you get a negative test statistic, then you find the area to the left. In either case, once you find the area either to the right or the left, you double it for a two-tail. But in our case, we've got a one-tail, specifically right-tail test. So we know that our test statistic is positive 3.614, and we want to find the p-value, that is the area further to the right on our t-distribution. We can do this in two ways. If we use the t-distribution table, we can't find the exact p-value, but we can find a range, and what you'll see when we get to actually conducting full hypothesis tests is the range is usually good enough. The other thing we can do if we want to get a specific p-value, as is asked on the homework many times, such as this example, we can use a spreadsheet. So let's look at the t-distribution table first. Some things we're going to have to keep in mind is our degrees of freedom, which is n-1, and that is 6, our 6 copper surfaces, our sample size, minus 1, so our degrees of freedom is 5. Our test statistic is 3.614, and it's a one-tail test. So what I'm going to do is, looking on our t-distribution table, I'm going to go to row 5, that's my degrees of freedom, and I'm going to look for 3.614, my test statistic. Now I almost never will find it in here, but I can tell that it's between these two in row 5. It's bigger than 3.365 and it's less than 4.032. So that means my p-value is going to be between these two areas for those columns. And I'm looking at 0.005 and 0.01 as opposed to this 0.01 and 0.02 because we know this is a one-tail. It's a right-tail test. So I know at this point that my p-value is between 0.005 and 0.01. And like I said, oftentimes that's enough. So my p-value is between 0.005 and 0.01. I don't know what it is specifically, so if I want a more accurate value, I can use some sort of technology, in our case, spreadsheets. So let's go take a look at a spreadsheet. Now I'm going to use the function tdist. There are many, maybe not many, there are several different functions related to the t-distribution. I'm going to focus on just tdist right now, but feel free to explore the other ones. Tdist, the first thing I'm going to plug in is my test statistic, 3.614. 614. Double check that. 3.614. The degrees of freedom we had was 5. And tails, I know this is a one-tail test. And that gives me 0.007. Let's call that 77. So my p-value is 0.0077. It's indeed greater than 0.005, but it is less than 0.01.